Okay, Micaela has a master's degree and PhD in industrial chemistry from the University of Bologna. The main topics of her research activity are preparation and characterization of novel polymeric materials with peculiar final properties, polycondensates such as polyesters and polyamide composites, and nanocomposites. She is co-author of more than 50 publications in peer-reviewed international journals, and you are, Micaela, involved in 3 Horizon 2020 projects, NOAP, Prolific, and Usable Packaging. One of them will be presented today, which is Prolific, and the title of your talk will be Ultimate Exploitation of Agro-Industrial Residues, a prolific contribution to the development of biocomposites. Now, finally, Micaela, the floor is yours.
Thank you. Can you hear me?
Yes, everything is all right.
Okay, thank you. The Prolific project that I'm pleased to present today concerns the extraction of proteins and bioactive molecules from wastes coming from legumes, fungi, and coffee. The project started on September 2017 and it will end on the next November. The project is highly applicative. The research activities and the partner of Prolific are strictly connected with the industrial users who know the customer demands, but also the technical constraints of their industrial sectors. The consortium is composed by 17 partners coming from industries, research institutions, and universities of 8 European countries. And the goal that the consortium wants to achieve is the production of 16 prototypes and to increase, to improve and introduce innovation in 4 industrial sectors that are feed, food, cosmetics, and packaging. The project aims to enhance those biomasses that are scrapped, discarded, because they are not food compliant or they are processing waste, such as the case of coffee silver skin. These biomasses are rich in valuable compounds, as for example, proteins and fibers, carotenoids and phytosterols in case of legumes, proteins and chitosan for fungi, and polyphenols and caffeine and fibers in case of coffee. So the project, this is the core of the project. Prolific applies a range of extraction technologies which are performed in a cascade approach to recover all the just mentioned molecules, biomolecules, for the application in these 4 sectors. And the packaging involves me directly, me and my group directly. In particular, within the project, on legume chickpeas and legume peas, an extraction process named environmentally friendly aqueous extraction was developed by SICA to recover proteins that were subsequently used in the food sector to produce protein flakes, protein pasta, protein bread, vegan burger, and so on. And the residues remaining after this extraction were used by Unibo to prepare packaging. On the other hand, the partner Celabor applied a cascade approach of various extractions on legume green beans. First of all, the supercritical CO2 extraction to recover carotenoids and phytosterols that were used in cosmetics sector for toothpaste and cream. And then this extraction was followed by a subcritical water extraction to recover polyphenols. And we used polyphenols to produce smart packaging, such as antioxidant coffee capsules or rigid antioxidant rigid jar for cosmetic, or a flexible film for meat products. And the residue was further treated by an alkali process and to give the fibers. And then it was subjected to another bleaching process to produce more resistant fibers. So all these residues were used in Unibo to produce packaging, and this extraction, the environmentally friendly aqueous extraction, was killed by a bio-based Europe pilot plant partner extraction, and also the residue was again tested by Unibo. The same cascade approach was used also on the coffee residues. Celebor applied the supercritical CO2 extraction to recover phytosterols and caffeine, and then the subcritical water extraction to obtain polyphenols and caffeine, and also the bleaching process to have cleaner fibers. Instead, the Spanish partner Iris applied a different extraction process, the ultrasound assisted extraction process, and therefore to recover polyphenols and protein, and therefore we received in Unibo 3 different residues coming from the same feedstock, coffee silver skin, that differ in terms of chemical compositions, because they were subjected to different extraction processes. Then again, Celebor tested the cascade approach also on coffee green beans, but he tested also a previous defatting process to eliminate, to remove lipids in order to have more efficient extractions after this treatment. And on this cascade, also the liquors coming from the alkali treatment were saved, dried, and sent to Unibo for the packaging applications. Before beginning our studies, all the received residues were subjected to thermogravimetric analysis in order to test the thermal stability of these residues, because TGA records the weight loss of the material by increasing the temperature. Probably you know, for sure, you know, when a material is exposed to high temperature, it degrades, it tends to degrade, producing volatile molecules, and therefore the material loses weight. So after an initial loss of humidity around 100 degrees, all the residues degrade according to different degradation steps. But in any case, they are all thermally stable up to 170 degrees. So TGA define also the chemical compositions of our residues, but its reading is not easy. It's easier to consider their derivative curves. and to further simplify its reading, we can initially consider only the TGA derivative curves for legumes. Okay, you can see legume chickpeas degrade in a single step. Legume peas in a pale green degrade in two different steps. This means that the chemical composition is different. Instead, legume green beans in dark green degrade seems to be the least stable with this curve located at a lower temperature, but its counterpart, bleached legume green beans, reported here in the dashed line, degrade in a well-defined step located at higher temperature. This means that the bleaching process removes the less stable substances, molecules, and therefore is a process that reinforces the residue. And this was recorded also for coffee silver skin, that is reported here in brown lines, solid coffee silver skin, and dashed the bleached coffee silver skin. And you see the bleached are more stable, and degradation occur at a higher temperature. No differences were recorded for the fatting residues. I mean the coffee green beans and the fatted coffee green beans. After this consideration, it's important to note, to observe that the coffee silver skin provided by Celebor in brown, this brown curve, is the least stable residue. Instead, the coffee silver skin provided by Iris in the yellow curve is the most stable. So probably the coffee silver skin provided by Iris contain a larger amount of lignin derivatives like phytosterols, depending on the different extraction process, that are more thermally resistant. And this is a good thing for the final materials that we have to produce. Okay, once the thermal stability had been defined, in Unibo we proceeded with the valorization of these residues by using them as a filler in the biocomposites. As a polymeric matrix, we have chosen the PBS, polybutylene succinate, that is a polymer biodegradable and biodegradable. And this polymer is characterized by low melting temperature, around 120, 140 degrees, depending on the formulation of the producer. This is a very good characteristic of PBS, because with this low melting temperature, we can process the polymer at a low temperature, and this means that we can save cost and energy, and also we can protect, we can preserve the fibers that degrade at a higher temperature. We prepared composite without any additive by simple mixing the PBS with the residues at 140 degrees. And we used different amounts of residue, ranging from 5 to 30% by weight. First of all, we analyzed the molecular weight of our composites, because sometimes the fillers could promote some degradation reactions. So it's important to verify the molecular weight of the polymeric matrix contained in the composites. And the molecular weight remain fairly basically constant for all the composites except for legume green beans. That therefore are not good fillers for our matrix because probably promote some degradations. In any case, the highest molecular weight were achieved with legume chickpeas and with the coffee silver skin. Concerning the thermal stability, you see the thermal stability decreases for all the residues by increasing the amount of the filler. But in any case, all these composites are very stable, thermally stable, with the temperature exceeding 360 degrees. So they for sure can be further processed, transformed at a very high temperature without any risk of degradation. And finally, very interesting, the results obtained with the coffee silver skin in a yellow bar provided by Iris that result to be able to increase the thermal stability of the matrix. And finally, the mechanical properties. I reported here the tensile results. You see there is an increment in the Young modulus and in the stress at break and a deformation and a decrement in the deformation for all the residues. And this trend is quite usual when there is a poor compatibility between the polymer and the filler. In any case, this worsening is quite limited, in particular for legume chickpeas, for coffee silver skin, and for the liquors coming from the fatted coffee green beans. So they appear to be the residues that produce the highest deformation at break. Even though the residue is present in a fair amount. I mean, 5–10% by weight. These composites, although obtained with a moderate filler loading, still maintains the PBS flexibility. So, in conclusion, we prepared biocomposites based on PBS containing up to 30% by weight of residues, and we demonstrated the feasibility of ultimate valorization of residues remaining after the extraction of bioactive molecules. When we consider the mechanical and thermal properties of these composites, you know there is a worsening in the properties, but this deterioration is limited if you use a reduced amount of the filler, and in any case, all the materials are biodegradable, bio-derived, and are cheaper because they contain a lower amount of the polymer. And finally, the composites based on legume chickpeas, coffee silver skin provided by Iris, and the liquors coming from coffee green beans are the best performing composites because they show properties similar to PBS. They are residues that maintain, able to maintain the main properties of the PBS matrix. And to finish, I want to highlight that within the project, we had the possibility to scale up some extraction process, and the residues coming from this scaled extraction were used by Unipisa to produce scaled composites for the prolific project. And this collaboration allowed us to use high-performing biocomposites and successfully close the loop of the circular economy. This is all for me. Thank you for your attention.
Thank you, Micaela, for your speech. The floor is open for questions. Any question from the audience? Well, I have, Beatrice.
Can I ask if you have some indications regarding the dimensions of the fillers that you have used?
Okay. Yes. The dimensions are about 300 microns. We have tested the granulometry, and we observed a size distribution, but the main part of the residues are larger than 200 and up to 300 microns.
So you obtain this kind of final particles without performing any grinding or granulometry reduction?
Not with our instruments,
okay.
with our equipments.
Okay, so it is like the material is obtained from the residue of destruction,
yeah.
Okay, without any other step.
Exactly.
Okay, thank you.
You're welcome.
Thank you. Any other question? No questions. So thank you, Micaela, for your presentation.